experiments in one lab. They have not been done like that. Like early this morning, I showed some of the micro-textured regions work that was done by Woodfield in GE Cincinnati. So that is one piece of work coming from there. And then these guys are fellow of the Proceedings of the Royal Society paper. They published some things, right? Let me also show you that. After this one, I will show you that paper. And then, so the bottom line is this, that titanium alloys do creep at room temperature, but they do have, it's only primary strain, very small amount of strain that happens at room temperature, or even at 120 degrees Celsius. So the question comes up is, does it have a relationship with dwell fatigue? Because when you are holding the fatigue cycle for that 60 seconds at the whole time, will creep take place? Will that primary strain contribute to the overall fatigue life going down? That's the question that nobody knows how to answer that question, right? I just showed you some micrographs that Neeraj and Glendane and Mike Mills did. Nice planar slip bands. And why the material creeps at room temperature, but it does not give you an answer for dwell fatigue. We have to make that connection somehow, and we are not able to, right? That's the problem. And then somebody's asking a question. Yeah.
You think that if we put the airplane at high temperature, titanium alloy, and we bring it at lower temperature, oxygen tries to go inside the plane. Is there can we fit to this way also? Is there any relation between this oxygen coming and causing creep?
It all depends on how high a temperature always, right? What temperature does titanium absorb oxygen in solid state? That's the question to ask, right? Normally, when we put hydrogen into titanium at a high temperature, it's quite high temperature. It's not the melting point, but it's still quite high. 800 degrees C, 700 degrees C, something like that. But you're not reaching any close to that temperature. Titanium has got a very high melting point, extremely high, right? Does anybody know what the melting point of titanium is? 1660. About that, 1600 degrees Celsius. You're not taking the airplane any close to that. You're taking the airplane, maybe the compressor and the fan maybe don't go above 300 degrees Celsius at the most. So we are only using that material because it's lightweight. We don't need nickel there, which is heavier than titanium. And we don't have anything in between aluminum, magnesium, and titanium as far as metal is concerned. So that's why we are using that, right? I mean, that's what I think. I'm sure there are more answers to that. So I don't think that oxygen will bother it so much. But if you go to a higher temperature, yes, you will absorb the hydrogen. And oxygen both. If you go to a higher temperature, definitely. Yeah, if you bring it to room temperature, yes. There are situations like that. I can't talk on the camera. Yep, okay. Okay, we looked at some of that stuff. Let me just come out of this for a second and go to this Royal Society paper that I was talking to. So there is this paper that I was talking about. The very first paper, I just sent it to Amit. He'll make a copy of that to other people. Adenstead, 1949. Creep of titanium at room temperature. It was published in Metal Progress, and it's two-page paper, 658 to 660, two-page paper. And Amit said he'll be happy to get that paper and put it in the final thing. That's a interesting paper to read, huh? Okay. There is another nice paper right after that, 2003, Bach. Review paper, dwell sensitive fatigue in titanium alloys. Role of microstructure, texture, and operating conditions. Okay, I can also print this out. There is David McDowell and this guy. Okay, computational modeling of fatigue, crack formation. There are so many others. Vikas Sinha that I was talking about, Mike Mills, Jim Williams. Okay, so there are several of them. Yeah.
You have said that earlier we talked about ASTM E39, we have talked a lot about ASTM E39.
E399, yeah, fracture toughness.
So something has to be standardized system for measuring the
It depends on what the community thinks. I mean, what is the community that is working in this area? I don't work in this area that much, except giving maybe, talking when people are talking about it. ASTM is working on dwell fatigue. Okay, there you go. So they're developing a standard for dwell fatigue. Okay, do they have a draft standard?
Yeah, it is. Complete. They made it actually. It is, I think, 2617.
2617. Okay, wow, that's good to hear that. Oh, you're talking about creep fatigue interactions. Oh, yeah, I was a part of that. That's not 2617, but he's asking about creep dwell fatigue. Dwell fatigue. Now, okay, that's what I was saying before. We have to distinguish between dwell fatigue and creep fatigue interactions. Okay? Creep fatigue interactions are a little bit different from dwell fatigue. Dwell fatigue is a word that's being used by the engine community mainly for titanium alloys for this kind of a problem, specifically for this problem. But the creep fatigue interaction that you are talking about is for any other alloys, nickel-based superalloys, titanium aluminides. Actually, for the Cameron Nigbin is coming, right? Cameron and I and Ashok was the one who driven, Ashok Saxena, they're all coming to your meeting. We started that, and I was the chairperson for that. Ashok made me a chairperson, that's why I was there, for the developing that standard for creep brittle materials. I thought I showed you that paper. Let me go there. Hold on one second. Yeah, I just want to, there are all these terms you have to be, there's sometimes they overlap. Creep, crack growth. So this is the one we have, E1457. No, standard test method for creep fatigue interactions. Right? This is the one? Creep fatigue crack growth testing. Let me do the creep crack growth testing. This is the one. Creep crack growth testing. Okay, this is another one. So in this one, there is, let me show you, Google Scholar. Okay, here we go. Creep brittle So this is Cameron. I'm talking about Cameron Nigbin. So this is the one we did crack growth in the presence of limited creep deformation. This is the data that we put for the creep crack growth standard, this one, E1457. So this is a little bit different. This is a little bit different than the dwell fatigue we're talking about. This is titanium 6242, I think. Yeah. 2519 aluminum alloy and titanium alloy 6242. 360, 135 and 500 degrees C, up to 500 degrees Celsius. The testing. So this is a little bit different again. So there are so many different things. So when we are talking about dwell fatigue, we are only talking about this particular problem, Jalaj. We're talking about this particular problem that especially in titanium, near alpha titanium alloys, which we are not able to solve, but it's a very serious problem for the engine community. So because it's a problem and we don't know how to solve it, What we are doing is to do more inspections than necessary, just to make sure that nothing is wrong with the disk, the fan disk. And then we're also concerned about the over-design. Till we know exactly what is going on, we don't know what to do. Up until then, we have to go with over-design and also more periodic inspections. So if we pull all the data together so far that we know in this area, if we put a little bit of, actually this may be a good time to do it. So far we have seen that to solve this problem, what we are finding is titanium creeps at room temperature. That data point we have. We know that near alpha titanium alloys have these micro-textured regions. Let me see if I can pull out. This is, I think it's Adam Pilczek's paper. And then the Royal Society paper is talking about the rogue grains. This is the okay. And then we're talking about debit in fatigue life. Of course, this is in the front due to hold time. Right? And this happens in fatigue crack growth test, also in low cycle fatigue. This is Tarun Majumdar, I think, or Goswami. I think, I don't know who is. So that's what we have right now, okay? And right, I mean, I don't know if we, again, if we have to have a test standard, it has to come from people like DMRL or AFRL, you know, Air Force Research Labs guys. Those are the guys who have to propose, saying that, hey, this is a real issue, let us develop a, a test standard.
We did that.
Huh?
Not in terms of test standard, but we try to solve it using some other technique.
Right, right.
Once you will finish, I will say.
Yeah, yeah. So I think that's, that is the data points we have so far. You know what I mean? Let's, okay, I'm going to close this, not important. So this is the Williams paper that I talked before. It's here. So this is all the data that we have. Again, beautiful micrographs, titanium, near alpha titanium. Critical resolved shear stress is a function of temperature. And there is the critical resolved shear stress, compression tension. Okay, so anyways, let me go here. But let me pull up the, not this one. Okay, this will be there in the report, but this is only for mostly people who are very much interested in the fundamentals of dislocations. Again, very fundamental things. I don't think I'm reading it. Does anybody is reading this one? Okay, so. Okay, here is a crystal plasticity models have been applied to cold well fatigue. I can show you that. Why does the addition of moly suppress cold dwell fatigue? So there have been experiments to show that, okay? And there are some explanations here, possible explanations. Let me put up here. Possible explanations are that moly forms complexes with vacancies, you know, and all the stuff. Why does raising the temperature to only 200 degrees suppress cold dwell fatigue? So there are all these questions, but we don't have the answers. Okay, it's more questions than answers. So here are some experiments again done on 6242 silicon with the three-point bend samples. Let me put this up. There, in titanium 6242, no dwell fatigue was observed at room temperature, right? Yeah, and for hold times of 60 seconds. No time dependence and only fatigue dominated, you know, crack growth. But when you go to, who was asking me about difference between cyclic and dwell, right? So here is a graph that shows the, on the left side you have the graph for pure fatigue. The dotted line is for pure fatigue, and the solid curve is for the dwell fatigue. You can see the differences in the number of cycles to failure, right? And this is, this one is 2 minutes, 2 seconds, 2 seconds. So 2 seconds going up, 2 minutes dwell, and 2 seconds coming down. And this is bimodal forging. There's so many variables, too many variables. Maybe design of experiments has to be done. I don't think anybody has done on this before. How are you going to resolve this issue? I have no idea. If anybody's got some ideas, you know, you can, but because see, this is a good difference there, big difference in the dwell and the cyclic fatigue. Unbelievable difference. 2,000 cycles it fails here, here it goes up to almost 10,000. Sample taken from the central portion of the forging. Okay. And again, dwell fatigue led to more cleaved alpha grains. Now I want you to be careful that cleaved alpha grains are the same as the slip band, same as slip band cracking. Remember, we put up on the sheet all that stuff, all those things. This is the titanium 1100. The reason we call it as 1100 is because it goes to 1100 degrees F. That's why we call it as titanium 1100. Okay? And the composition is right there. 6 aluminum, 2.7 tin, 4 zirconium, 0.4 moly, 0.45 silicon. Okay? Lamellar microstructure. Can somebody tell me as to why this lamellar structure is so different looking than normal lamellar microstructure? Bhanumati, you should know that, right? You have an answer? I mean, I'm just wondering. It looks a little bit different, right? Yeah, but it is a lamellar structure in 1100. Solution heated at 1868 for 30 minutes, air cooled. There is a prior beta gain size, and there is the lamellar, you know, spacing. Okay? Let me know if you know the answer. It kind of looks to me like it's not fully developed lamellar microstructure for some reason. It's not fully developed.
Lamellarity is not developed properly.
Huh?
The lamellarity is not fully developed.
It's not fully developed, yeah, yeah, that's what I think, but I don't know why, because the heat treatment is all done properly. Huh?
Sometimes the fine lamellar structure which we can resolve only at high magnitude.
Okay.
20x,
Okay.
20,000x.
Okay,
That time it looks like that.
okay,
This kind of structure we have observed.
okay. So if you go to low magnifications, you will see that,
High mag.
Okay. Okay. So I got all these things in for you. There is yeah, Goswami, not Majumdar, or not Majumdar, yeah, Goswami. So he did some low cycle fatigue, these kind of dull fatigue, right? So basically, you're holding it here instead of holding it at constant load. This is a constant load, constant stress, constant K test. Here, it's a low cycle fatigue test, and you're holding it at constant strain. And the load, okay? You're holding it at constant strain. So people are just trying different experiments to see if they can get to the answer. But to me, it looks like a, just a test without, I don't know the reasoning. Why would one, why this test would reveal anything more other than just giving you some answers, some things. A new dwell sensitivity damage parameter. So a lot of materials tested, copper alloys, super alloys, iron 100, it's a powder metallurgy titanium, Rene 95, wasp alloy, and then also there is a NAR alloy Z. That's a, oh, I'm using my mouse here. That's a space material, NAR alloy Z. Okay. This will be there. Okay, more of this. Okay, so let me go to, that's all what I have on this thing. But let me pull up a couple of papers here. Just to, I haven't made slides, but I saw some papers when I was talking to her, to Bhanumati here. One of them is, right, this one. There is the crystal plasticity model, okay? I wanted to show you this. I wanted to show you this equation here. You remember we were talking about the strain rate sensitivity parameter? So here is the, something like that, gamma dot alpha, which gives you the slip rate essentially. So this is your mobile dislocation density. This is the frequency at which the dislocations are trying to jump the barrier. Burger's vector, activation energy, right? Delta H, activation energy for self-diffusion. Okay? Boltzmann's constant. This is some temperature. Shear stress, corresponding critical resolve shear stress, tau sub C alpha.
From there, this data will be coming.
Huh?
Activation energy for self-diffusion. From where will be coming?
Where do you find it? I'm sorry, activation energy for self-diffusion in creep.
From where it will be stuff coming?
Where it will be coming from. So when you are doing your creep, let me draw this, maybe it'll be easier. So same thing, like he put gamma dot, okay? You can put gamma dot instead of epsilon dot, which is fine. Both are strain. Strain rate, some constant, exponential, minus delta G, that's what he used there, divided by KT. And some sigma here, sigma raised to n. So that is your creep strain rate. That's your strain rate. So let us say creep strain rate. Or if you want, it could be plastic strain rate also, no problem. Don't let it scare you. Same thing. This process, so this is a process, right? Because the strain rate is changing The strain is changing as a function of time. So there is a process by which it happens. So the process can be controlled by, let me put this on a piece of paper, on our paper. This looks like it's important. If I write it on the board, we lose it. Let me put it on the paper. Okay, base 3. Here is your thing. So epsilon dot, well, or gamma dot is equal to some constant, the stress on the specimen, exponential delta G over KT. This is your Boltzmann's constant, okay, K sub BT. This process is a creep process or some kind of a plastic deformation process. Is or can be controlled by dislocations. Remember, this is a symbol we have been using for dislocations or vacancies. If the temperature is low, again, low and higher relatively, comparison to each other. This is at relatively low temperature. This is a process at relatively high temperature, okay, where vacancies can move. Okay? Here, at this point, at high temperatures, it could be a self-diffusion. Let me put here, vacancies, vacancy movement. This could be by self-diffusion. That means this is a titanium alloy, right? Titanium aluminum. Let's say titanium. Or it could be a self-lattice diffusion. Or this could be a grain boundary diffusion. Right? So, oh shit. Okay. Grain boundary diffusion. Yeah. So we have a process like that, that gamma dot. I'll put it back again. So remember this equation. You have a load, activation energy. This process can be controlled by either by dislocations or vacancies. Let us say this happens at low temperatures. We won't consider that for right now. Let's consider this. Happens at high temperatures. This vacancy movement can be inside the lattice. So there is your lattice. There is my lattice, right? So it could be moving inside, inside. Okay, and it's going, by struggling and somehow going into the next, moving along like this. Or it could be grain boundary. So this one I'm talking about is this one, self-diffusion. This is grain boundary diffusion. Okay, so all these guys, Navarro, Herring. So this is cobalt creep. This is Navarro Herring. Or is it the other way? I don't know. One is one, the other one is other. So the activation energy that you need for this one is higher than the activation energy for grain boundary. self-diffusion. Which one will take place? Which one? This one will take place, this one will take place, this one will take place, that one will take place. It all depends on this temperature and this stress. That will determine which of these will take place. You can always argue. Actually, I'm thinking in my head after you asked the question, why is he talking about diffusion? He probably should be talking about dislocations, maybe. I don't know. Maybe he should be talking about dislocations and not vacancies, not self-diffusion. Because in titanium, we're only talking about 120 degrees C. That's all dislocation creep. So.
Diffusion may be due to concentration gradient. Due to concentration gradient.
Concentration gradient, yeah. What you're saying is true. It could be due to concentration gradient. Yeah. Purely concentration gradient, yes, it's going to happen. If you have too many atoms here, too less here, they'll start flowing up and, yeah, from the hill. Yes. Yeah. You're asking tough questions. Fundamental philosophical, fundamental questions, which is interesting. Yeah. You're right. Diffusion is taking place because of a gradient in concentration. This diffusion is contributing to strain. I'm going to make something up. Somebody, you're asking questions, I'm going to make up an answer for you. I'm going to write this equation as d epsilon dt is equal to a sigma raised to n exponential minus delta g over kt, right? So my epsilon, d epsilon, sometime t1, or epsilon 1 to epsilon 2, that is my increment in the creep deformation, is a function of, I have a constant stress. This whole thing is constant. This whole thing is a constant. Constant temperature test, constant stress test. My process is same. Everything is a constant. I want to put here constant dt. So A prime t is equal to epsilon . Oh, well, I may have to put here sigma, maybe. I don't know. I'm going to make something up. You said concentration gradient. True. I'm just going to put, if I have a little volume element here, this epsilon, this d epsilon that will take place, this volume element, d epsilon, will be taking place because of a stress gradient, sigma 2, sigma 1. Okay? Inside a small zone inside that component. So you can, but the point is this, and that is taking place due to your. Yeah. So instead of concentration gradient here, the vacancies are being driven by a stress-assisted diffusion. Right? Remember the Fick's law, law number 1 and law number 2. The law number 1 is what you just said, diffusion code. Yeah. And the second one could be a stress-assisted diffusion. Yeah, I think so. Yeah. Or Kumar Jata's second law. No, it's fixed. Okay, so basically this is your, so that slip rate, let me just take out all this mess that I just made. So that slip rate is your creep. Okay, that is your creep essentially. That is d epsilon dt. You got mobile dislocations, rho m b v bar. Yeah. Yeah. You remember the equation? There is an equation, that is the mobile dislocation density equation. Rho mbv, epsilon dot is equal to huh?
There are two shear stresses in the equation.
Yeah.
One is resolved shear stresses. One more is critically resolved shear stresses. CRS.
You talking about strain? Oh yeah, yeah, this one. Yeah, yeah. Okay. Yeah. Yes. Then yeah, I mean a critical and then just a yeah. Yeah.
He's asking the
Difference between that? Well, one is the critical, one is not critical. Right? It says critical. No, I mean, you see what I'm saying, right? I mean, in order for a shear strain to happen, you have to have a difference in shear strength. That's what I try to do here, sigma 1, sigma 2, to produce the d epsilon. Right? So here to produce the d gamma, you have a d tau. D tau, right? The d tau is equal to tau minus tau critical. Right? So don't make this mathematics too harder, as hard as Ramanujan's mathematics. It's not anything close to it.
It is the same way, sigma ys and sigma. Sigma yields and the
Yeah, yeah, sigma is equal, tau is equal to sigma divided by 2.
similarity.
Yeah, yeah,
Sigma critical.
right? Tau is equal to sigma.
Within the plastic region also, but plastic region we are taking the strength, shear strength, whatever. Within the region of plastic region.
Yes, yeah. Creep region, yeah. Or plastic region.
Plastic region.
Or visco, yeah. I mean, a gradient in, yeah, a strain d epsilon has to take place because of, either because of the gradient in the, in the atoms or vacancies, something like he was talking about. There has to be a driving force, right? Either a concentration gradient has to drive the diffusion, or in this case, a stress diffusion, a stress-assisted diffusion, right? See the gamma dot that you're obtaining here, the slip rate, that could be a plastic slip rate if you're talking about plastic, or if you're talking about creep, it's a creep slip, deformation rate, but that has to take place because of the, some kind of a tau, delta tau.
Once it tilted, the shearing stresses will be developed in that region.
Yeah. And this is nothing but, this part, rho sub mbv, is nothing but epsilon dot. Or you can put as gamma dot. If you put it gamma, you'll put what? Twice or something? Or epsilon is equal to 2 gamma. Right? Yeah. And I don't know where the hyperbolic comes from. Okay. So that is basically your crystal plasticity model, essentially. Beginning of the crystal plasticity model. Okay, that's one equation I wanted to show you, 2.1. These are all the efforts that are being put into understanding dwell-ready. You can make it more complicated than what it is. Yeah. You're trying to make it more complicated? Go ahead. Yeah. Go ahead. Yeah.
Sir, I referred in theory of plasticity by Slater. He was whatever he mentioned. That's what I'm asking.
Slater?
Slater.
Slater. Oh, okay. You're following Slater's book? Good for you. I don't think I will understand the book, so I leave it to you. No, okay, yeah. So, so here you got that, see, there is your critical is equal to some nominal number. You see this one? You're seeing it on the computer, okay. So there is that same equation that I wrote there. epsilon dot is equal to GMB, epsilon dot is equal to rho MBV. That's the same equation as this. That's the same as this. Okay? Only thing is that dislocation density has now been broken up into statistically stored dislocations and geometrically necessary dislocations. So now you have to go up and look up what those two things are. If you don't remember, then you have to start looking at those two. What can you do, right? But that's your crystal plasticity, beginning of those things, right? I just wanted to show you this, you know. Then you go into matrices here, make it more complicated, matrices, you know, transpose and regular matrix. Okay, this we don't need that much. All the parameters are here. All the parameters are there. Mobile dislocation density, initial dislocation density, frequency at which the dislocations are jumping each time. You know, Burger's vector, Boltzmann's constant, of course, strain rate, starting strain rate, some initial strain rate, some, you know. Critical resolved shear stress of the basal, for the basal plane, activation, comma prism. Yeah, either one of those, not pyramid. I was worried that it was pyramid. It's not. Okay. So you got all these numbers there to crunch and grind that equation, you know. So you have to look and see why these guys are doing all this for dwell fatigue. That's the thing. Because the thing is dwelling, I mean, not dwelling, the thing is deforming, right? Because during dwell fatigue, we are getting some creep is happening, which can happen in room temperature at low degrees. So that strain that is coming along is because of that equation there, okay? So he's just making it a little bit more, he's from University of Cambridge, so he's making it a little bit more complicated. Not because of that, I'm just saying it's a little bit more complicated. But it's more realistic also, okay? So, and then, okay, those are all modulus and G. So he went up to 300 degrees Celsius. Change up to 300 degrees Celsius. I'm actually reading this paper as you live right now, okay? I'm just reading it as I'm going along with you. So, and here is our Williams work, the classic work. This is a great piece of work, very, very important, right? The pyramidal slip has got a higher critical resolved shear stress compared to the basal and prism. Oh, okay. It's actually an interesting paper, it looks like. A little bit of finite element analysis. There's a hard grain, there's a soft grain. So now your question of, who was asking that question during the break, how are you going to transfer the slip, you know, from the soft to the hard and the hard to the soft? This probably will answer some of those questions. If you do the, So we defined, right? So for example, the basal plane and the prism plane require much smaller. Let me get to the figure. To get these guys activated, you need a much smaller stress. But to get to this guy activated, look at how much the big difference is. So this is the harder mode, softer mode. So that's the complexity of gamma. I mean, HCP microstructure. A little bit more difficult than the normal FCC, BCC crystal structures. Because you got this pyramidal plane, basal plane, and prism plane for slip. It makes it more complicated. So all I want to do is to basically leave you with the idea that the dwell fatigue is still not completely understood, like we're saying. There are a whole bunch of data points. how do you pull this data together and try to make an understanding? I don't know. I mean, I think it will require some effort for somebody to understand this. If you have a whole summer available to you free to nothing to do, I mean, it's a good time to take a problem like this and do it and work with somebody who knows what they're doing, right? So, yeah, it's a lot of, yeah. Okay. Okay, so there were some questions before. During the break, somebody was asking, do you still have those questions? Who has those questions? No, everybody's quiet. Now, during the break, 5 people show up, and so make a list of your questions. Maybe tomorrow is Tuesday. No, today is Tuesday. We have Wednesday and Thursday, 2 days still left. So if you bring your questions, make a list of the questions, actually. It will be much more, instead of just shooting off questions as they come to your mind, instead of that, just kind of make a list and bring those questions, then we will try to discuss them. I may not be able to answer everything, but we'll answer them. Yeah.
Sir, we want to discuss about the real case studies if you have some.
Oh, yeah.
We are doing
Yeah, all the theory and all that, yeah.
Any real?
Yeah, let me do one thing, because you're asking live, so let me see if I have something here. Okay. In my save. Okay. Spring. Let me see. I think I had it here some. For okay. BC10. Well, this is this volume 11, ASM Metals Handbook, Failure Analysis and Prevention. Write that down. And if you can get it, try to get it. And let me see if I can pick something here. Then we can, let me say, find. Creep failure. Okay, creep failure. Let's put this one. Super alloy. Nope. Okay. Huh?
Don't feel bad. Generally, we are always using ASTM, ASM, handbook, and everything.
Yeah.
We are not using Indian standards. Why, sir? What happened? Our Indian standards.
No, there are a couple of guys who wrote very good books, actually.
Yes, sir. That's so many people, sir. An example I have given for books also. Update analysis by processing, and what so many people, sir, and also one more book is there. Yes, also Indian authors. But we are always referring foreign authors. What is the difference between Indian authors and foreign authors?
No, it's just a compilation of the failures that are taking place that American Society for Metals has taken charge of. But you're ready to, you can do that for another, you can, no, I don't mean in a bad way. You can start a editorial group and bring people together. No, really.
You are referring ASTM, ASM, always America, where the
No, you can do the same thing.
America, sir.
No. No, you can, I'll tell you what, here's a challenge. Next time I'm going to come, I want you to be the editorial board head of the Indian Failure Analysis Handbook. No, seriously, start doing that. I mean, just because there are more people who are working in those areas, that's all.
But your research told research in America or India, what is that?
No, I think I agree with you, but somebody has to take, but there are very good Indian failure analysis handbooks. I'm trying to think of one author, IIT Madras guy, he retired, Reddy. Janardhan, some Reddy, yeah, not Janardhan Reddy, but some Reddy. He used to be a DMRL. Huh? There used to be a DMRL, I think, that Reddy, who wrote a book, or IIT Madras, one of the two. Yeah, failure analysis, put failure analysis and, yeah.
ASM, ASTM also, it's not only Americans are there as a member. It's worldwide people will be there who's over leading in. And
Yeah, there is everybody here.
What the name indicates American?
I don't know. Huh? A.N. Reddy. Okay, J.N. Reddy. Failure analysis. Yeah, doesn't matter. Don't worry about that. Look here, I'm coming all the way from there as an Indian, not as an Andhra Pradesh guy, okay, please. No, don't even bring that up, that's wrong. Okay, but it doesn't matter where he's from. He's an Indian, right? But that's not the point. I'm talking all these things in YouTube. I shouldn't be talking, okay. Can we edit this, please? He's going to get me into trouble. No, but that's a failure analysis book. And he has written out of a lot of experience, right? So there you have, right there. I want you to buy a copy of that. So here is here I just put in, अरे यार उसको aid करना पड़ेगा, seriously. I don't want somebody to be, okay. So I just put randomly, I put creep, I think, and I put superalloy or something, and this is what showed up in my search, okay? And let me see, is that what I put in find? I don't know what I put in. Okay, but this is what it showed up. So here is an example of a thermomechanical fatigue cracking and oxidation in a first stage turbine blade. Okay, so you can look at let us see if there are any given conditions here, for instance. Okay, here, that was what, figure number 4, right? Okay, figure 4. Figure 3, okay. So there is my figure 4, there, thermal fatigue. So you can read about thermal fatigue right there. It's a real problem. So thermal strains are generated in airfoils because outer surfaces change temperature more rapidly than the metal within. In turbine foils, creep strains are superimposed on cyclic thermal strains, and thus account for a further reduction in life expectancy. So basically what we're talking about is, what is that equation? So, you can always put an equation down for everything that's happening around you. So you got a strain that's happening because of, I think I did this other day, thermal expansion coefficient, E. delta T. So the strain that is being developed due to the thermal strain that's developing, this is the thermal strain that is developing, is due to thermal expansion coefficient difference, maybe delta alpha, maybe there's a delta E modulus difference between the coating and the blade, and then the temperature difference. That's your thermal. And on top of that, you have the mechanical strain, right? So mechanical, if it's elastic strain, all you do is by, right? What is that? Young's modulus is equal to, I have to write this down usually, sigma divided by epsilon, sigma divided by delta E, if that's the case. But this will be E in this case. So basically, you are getting those cracks because of that. Okay? That's a typical example you have. Now, when yesterday, Battery-wala, what is his first name, Rajesh or Ragesh Battery-wala was talking about coatings. So there is your, where is my, so there is my base material. I can tell because I can see some microstructure. And there is my bond coat. And there is my top coat. Okay? You can see clearly the regions. So, of course, there's polished metallographically. So, but the hot gases were coming from here. So this is the low magnification. Whenever there's a failure analysis, you should always start from a low magnification, either 1 or 2. So here is the picture of the airfoil. Okay? That's the airfoil or the turbine blade in this case. Okay? Turbine blade, airfoil. And when somebody gives you this, you should always ask which blade number it is. Was it the first stage, second stage, third stage? How many stages were there in that turbine section? Okay, just basically some of those things. And they won't tell you probably what coating it is, but you can see the coating has, in the second magnification, you can see, oh, they put a ruler here. How nice. That's an inch ruler. Oh, that's the only problem. So 1 inch, 2 inches, 3 inches. You don't use inches, right? 1, 2, 3, 4, inches like that. Okay? And then you take this thing. You can see a crack right there, right? And then you make it a little bit higher, and there is that arrow still here. And then you make it still higher. Okay? Then you can see that, this is just a metal, just something. So the crack is there. It came through the top coat and went into the bond coat and went into the material. Okay? So, and you can look at this. If you want to break it from here, of course, you have to ask the permission of the person who gave you this. And you can break it open totally. And then you can look at this fracture surface inside. But that's not important. The important thing is it broke this coating, which is supposed to be protected. Because this coating was supposed to protect your base material. So the important thing is that this was jeopardized during operation. So what you want to find out is how many cycles it took for it to do this. What was the temperature? And cycles will be enough. I don't think they can tell you the load and all that stuff. It depends on how deeper they want you to solve this problem. Okay? Yeah. So here it says, so basically now you can do all kinds of things with this crack to see. You can still go to higher magnifications, You can still go to higher magnifications and see if there's any oxidation deposits, any corrosion deposits. You can take it to the SEM and look at the analysis, what kind of deposits you're getting. And all you can do is to report those deposits to the customer who gives you this. And probably they can relay that to the guys who are preparing the coating. Okay? So, again, it depends at what level you are on. I mean, you know, the thermomechanical fatigue load modeling, models are available, but I think that's a little bit more involved. In the sense that a lot of times in engines, what happens is the mechanical load, so the mechanical load, let me erase this. Let me erase this, yeah. I want to take a couple more examples, so I don't want to sit on this for too long, so you can get a little flavor. Sometimes so there is your mechanical load, okay? The temperature load also, the thermal load can go like this also. Maybe not the same amplitude, maybe not the same amplitude or more amplitude, could be either way. This is my temperature. So they're in phase. In phase thermomechanical fatigue, or they could be out of phase. So when this is high, it is low, and when it's low, it is high. So this is your mechanical, your thermal. So out of phase. 1 second. So for metals, it may not, but you see the thermal gradients, how they are now? They're going to be very, very drastically different. When this gets to be high, this gets to be low. Okay? When this gets to be high, that gets to be high also. So the results will be completely different. The life would be completely different between this and this. And this can become really bad if you have a composite. This is a metal, so there's no problem. But if you have a composite like a silicon carbide fiber and a silicon carbide matrix, then because the modulus is going to be very different, then it will become a problem. But in metals, it may not make much of a difference, okay? But I wouldn't worry about it too much because we are just starting to use composites for engines. Very little, very little. Metals are still going to be around for a long, long time. But in a research fashion, that will be different. That will make a big difference in out of phase. Okay. So they both have models, their own lifetime. If you run the engine, how much that would be, how much life would this be, okay? So you can get more deeper into it. Somebody was asking a question.
In the load, what you are trying to show mechanical load, engine was started, stopped, or it was a constant operation of the engine. Mechanical load, how it is being put it. Engine was started, stopped, or engine was running all the time?
This is all the time.
All the time.
Yeah.
So thermal load should be constant because the gases will be passing through the blade all the time and they will putting constant.
No, you're asking a question that's beyond my expertise. I don't want to some BS something to, I don't know. This is more of a laboratory thing I'm telling you. But how in the engine it really takes place, if I told you, I'll be bluffing. I don't know, okay? Yeah, but in the laboratory, this is what we do, test a lot of times. We program it such that the load generator and the thermal waveform are opposite or together. So when we did the titanium SiC composite long time ago testing, we did those tests, and out of phase was much more burst effect on the composite. The fibers were getting pulled out in the opposite waveform. That's all what I'm saying. And, you know, yeah, go ahead.
In the first line, he's saying that at the end, the plane of maximum stress and the crack are perpendicular. So how we can say that the crack are perpendicular, that maybe in the same load will also be acting in this direction and the crack may also propagate in this direction.
Right, so the crack, what happened? Oh, yeah.
But here it is written that then propagate oriented perpendicular to the surface and plane of maximum stress.
Yeah, it's okay. Nothing wrong with that. The stress is perpendicular to the crack. It's okay. That's the way it should be.
It should be.
Yeah.
Suppose the crack is propagating in this direction
You mean at an angle?
This direction, sir.
Okay.
As it has shown. Plate
That's what is going, right? So this is perpendicular to the stress axis. Yeah, because the centrifugal force is pulling the blade out like this. Yeah. Is that what your question is? Yeah.
I was saying that stress may be in the same direction also, sir.
Oh, no, no. Stress is perpendicular to that. Yeah. So basically, this is one example, right? I'm just giving you an example of failure analysis. This is something that comes around quite a bit if you're working in the failure analysis group. Have you ever worked in a failure analysis group? So this is one of the common things that can come from the engine people to look at the engine people may send this part to you as a metallurgist, take a look at this and see, tell us what happened. Sometimes you can tell them many big story or sometimes a short story, depends. Okay, let me take another example. Okay, let's find something else. Are you okay with it or? Okay, yeah. And can you write down page 624? Okay, write it down. Maybe I can print this out for you later on as an example. Okay, let us take another one. Let's find something else. Tell me something that you guys think maybe something that tickles your. Bolo, yeah? Could be something, maybe a titanium. Oops. Let us see what we find here. Maybe nothing. Okay, it's not coming out anything. Let me stop this. Sometimes if you give too much, it won't be able to read. Oh, let's go to the index, actually. Sorry, what am I doing? A lot of times we cannot show failures outside. We cannot show any of the failures that are happening in an organization to outside people. We're restricted from doing that, because we don't get permission to do that. But we can. This is open book, so we can look into this one. The first ones are all very, very good things to read. Actually, reliability-centered maintenance (RCM). Okay, let's see. You want to look at something? Let's look at Aloha failure. What am I talking about? Let's go to Aloha failure. Okay. Or United Airlines. Okay, yeah. Why don't we do that? Aloha Airlines failure. What happened? Airlines 88. Okay, there we are. आवाज नहीं रहा है आवाज नहीं है Okay, well, do you all know, are you familiar with this? Right? Everybody is familiar with this, right? Familiar with this? Yeah. They missed the NDE inspection on this. That's what I remember. Let's see, one second, let me go here. Group, individual. Aloha, Southwest 1380. This was spring. No. Give me 1 second. So this is the failure that recently took place, Southwest Airlines. Just recently, it came in the news actually. Yeah. No, this is an old one. Is it? There is a 2018, April 17, 1318 flight 737, left engine failure, sudden depressurization, and I think one person was killed, I think. 8 injuries and 1 fatality. Okay, 1 person passed away, died actually, because I think what happened was, let's see, left engine failed, inlet cowl. So this is the cowl. Let me see. This is the cowling. This is the cowling. The engine is inside, engine cowling. Okay. So sometimes what happens is, what can happen is, I've seen some of them, if one of these blades will fail in a very serious way, it can come through the cowling and hit one of these places also. It depends on the angle, where you are and everything. So if this is rotating so fast, the blade can come out, and then hit this cowling, break it open, and then go through it and hit the airplane. If there is somebody sitting here, it can take that person out too. Okay? That has happened before. So on this particular Southwest airline, this is all the description. Lower aft. Let's see. Okay. Number 13, fan blade broke. Okay, due to metal fatigue, essentially metal fatigue. Several areas of fatigue fractures were looked at. Okay, and then you see it's all details are given here. The origin of the crack that broke ½ an inch from the leading edge. It started on the convex side because the blade is like this usually. The blade is usually like this. Okay, it's like this. So this is your concave side, and this is your convex side of the blade. Okay, so it started on the convex side and extended ½ inch deep into the dovetail. So dovetail is, so this is your dovetail. So there is your blade. Well, okay. So this is your dovetail here. Okay, so the convex side is back, concave side is front. 2.3, okay, ½ inch into the dovetail actually. Wow, that's pretty long, right? The total length of the feature was 2.232 inches long feature. So you just keep on, there is the fatigue origin. This one? Beautiful picture of see, this is exactly nicely looks, how nicely it looks that feature. Of course, it's a bad accident, but see the fatigue, how it proceeded? And that's the overload right there. So this is all fatigue up until there at a low magnification. Let me see some other good eddy current. Okay. At the time of the accident, the aircraft was subjected to visual and fluorescent testing during its last overhaul 2012. So basically, you want to look at the records of the maintenance and see what kind of maintenance was done on this. They should have the records. They may not show it to you. The airlines will not show it to you if you're a private guy. Obviously, if you work for them, they'll show you. But if you're coming out as a consultant and say, hey, I want to see your records, they'll say, go and take a walk in the park. They won't show you. Okay. So fluorescent penetrant inspection. So a lot of times what happens is the cracks are always closed, okay, unless there is a load to open them. But whenever there is an accident or anything for that matter, the crack is always very closed, and you can see that very, you have to look for it a long time. But instead of that, if you do FPI, fluorescent penetrant inspection, FPI, That's the first thing you should do always. Okay? You put the fluorescent inspection dye, it's liquid, you put it on that, and you take it to a dark room, and you put an ultraviolet light. If there's a crack, it will glow like a straight line. It will illuminate purple color, and you will see that there is a crack. Okay? So that's what, so they may have missed if there's a crack there, they probably didn't see it. There was a small crack, they probably missed it. And then there also, so that's the first line of inspection. The second line of inspection is eddy current inspection. Okay? Excuse me. So in eddy current inspection, there is a coil usually. So eddy current inspections are, I'm going to give you a rough figure right now. I may not know the details, but detail enough for us to go ahead with this. So fluorescence penetrant inspection is one of the NDE techniques. The second technique that they were following was eddy current inspection. In eddy current inspection, simply what we have is kind of a coil you have. It may not be, I don't think it's a spiral like that exactly, but something like that. And then you bring that coil near to a plate. So if I have that blade there, I have that blade, I'm just going to put a rectangle. And let us say the blade has got this crack there, and I brought the coil there, right? So I got something there, and there is also something that reads voltage or current and all that stuff. And then if there is no crack, the eddy current coil will, everything penetrates properly, right? But as soon as I have this thing, there are more number of, So if there are lines, if there are field lines, I'm going to put electric field lines. There is my lines, my electric field. There's no crack. But as soon as there's a crack here, these will get distorted. Just like your stress lines, these will get distorted.
In eddy current, we see continuous wave like this. Wherever the defect is coming,
Yeah.
it makes a great peak.
Right. So it will show a meter reading. Yeah. You're also talking about ultrasonics. When we come to that, we'll show that to you. Yeah. Okay. So eddy current coil, basically. The only thing is, if you have a surface flaw, so the eddy current frequency at which it works is proportional to the frequency of the coil. The frequency at which you're working. I don't think the people in the back will be able to see my small chicken. Okay. Frequency of is inversely proportional to penetration depth. Okay, so penetration depth. So if I'm looking for a crack which is on the surface, I use a high frequency because the penetration depth is low. Okay? So if I think that the crack is on the surface, I use a high frequency, so it will become very sensitive at high frequency, and it will detect the crack on the surface. But if I want to go deeper, I reduce the frequency. The electric field will go deeper. So the penetration depth is inverse of the frequency, right? Okay. So the first thing that you want to do with eddy current inspection is always use a low frequency coil and just kind of take a look at the forest from the helicopter. Instead of looking at each tree, then you increase the frequency and start looking at the trees, and you start looking at these flaws. Because we said fatigue cracks always start at the surface, right? Let's go back to that picture again. So in this case, what we did is to look at the Oh, did I do? Oh, yeah. I thought Beethoven was just. Okay, sorry, yeah, okay. Oh, okay. We're on the. Of course. I thought you were playing music there. Sorry, that's okay, okay. So the plane was also visually, so all these things were done. Eddy current inspections were done. The dovetails were, the wings were lubricated 6 times. So because if you don't lubricate the root of the blade, because the root of the blade is sitting in the disc, and it's got a little slot there. It goes inside, right? So the blade will be moving like this, okay? If it's not, you got a bolt and everything, but still there's a fatigue, this way fatigue also going on. So the blade is vibrating like this, the blade is vibrating like this, and there's also a little bit of this thing going on between this surface, and the root it's going in, okay, this way also. Yeah, it could be this way, it could be that way, I don't know whichever way it goes. But the main point to remember is there's a wear fatigue also going on right there at the interface between this guy and that surface. Wear fretting fatigue. Fretting fatigue is nothing but when 2 surfaces mate each other and there's a rubbing going on at the same time with a certain frequency. That rubbing will produce wear debris, and it's called as fretting fatigue, because that's where the cracks will start. After a few cycles, it will start a crack. So that's a fretting fatigue crack. So far we saw axial crack, shear crack, torsional cracks. We didn't see them, but we didn't mention them here and there. But that's the fretting fatigue crack. So you always lubricate those surfaces to reduce the friction. So in this case, we use moly disulfide. It's a solid lubricant for the engines, okay? Because it's very stable up to high temperatures. So they were lubricated to take care of any fretting fatigue. And also the plane was visually inspected, right? Every time the pilot lands the plane, the 2 guys also before taking off, they just kind of walk around the plane and see if they can see any big cracks. Because you can fly a plane with a crack this long as it's not there in the fuselage. But because remember, the plane is made up of layers, right? 1, 2, 3. Thin sheets. They're put like this, right? The sheets are, they got 1, 2 lap joints, like a lap joint, right?
Sir, when an accident happens, then it happens spontaneously, suddenly.
Yes.
Then subsequently, other parts are also getting damaged. I mean, if one blade has got cracked.
Sure, I know what your question is. Go ahead.
How did they identify exactly blade number 13 was the...
Well, yeah. I mean, that's the whole failure analysis. That's why it takes so long. Your question is very valid. That's why it's like going to the doctor again. You have to know what is going on. Remember, the pilot is getting all the information. The black box is getting all the information also.
But it records the altitude and the conversation.
The loads also records. Altitudes it records. But engine health, that's what you're asking. Why blade number 135? How do you know, right? Most of the blades are intact. They're probably still sitting there in their places. Okay? Maybe a couple of them came out. Which one came out? Yeah, this is like a forensic work. It's like a, what do you call the inspector,
Keeping constant watch on.
No, what do you call the inspector here? There are movies too on it. Huh? Detective, yeah. It's a detective work. It's a detective work. Yeah, I know your question. That's what comes with experience, especially failure analysis. Yeah, there are some guys who are pretty good at it. If you keep doing it. Some people may get excited about this. The material was a Borsig fiber reinforced aluminum composite. Who was that who was talking about composites being used in the industry? Come on, during the break. One of you came during the, yeah, you were the one, yeah, exactly. So there, They're airplane parts, right? You see that, right? Yeah. Okay, let's go to the next page. NTSB is National Transportation Safety Board. They get always involved in every accident, especially if it's a civilian failure. National Transportation Safety Board engineers guys will show up with their bags. I think 5 or 6 guys are showing up. You know, the detectives are coming. So anyways, let's, you know. So what happens at a time like this? The Federal Aviation Administration will ground all the planes with that kind of engines, which are flying with that kind of engines and which are having 30,000 cycles, you know, there. So they grounded all the planes, no more flying with those planes which are carrying those engines, don't fly. That's the order. Everything is stopped. If they have 30,000 cycles on their plane, and let us do the ultrasonic inspection. So we said frequency, we said fluorescent penetrant inspection. That is number 1. Number 2, eddy current. Let's do number 3. Ultrasonic inspection. What is the human hearing range? Exactly. 30 to 10,000? 20,000 kilohertz, right? No, 20,000 hertz. Yeah, 20 kilohertz, exactly, yeah. So that's the range we can hear. And in ultrasonic inspection, we can obviously go up to megahertz, 10 to the 6, if you want, kilohertz, megahertz. And what is the principle of resolution? The principle of resolution is I can always resolve an object which is 1/4 to 1/2 of the wavelength of the wave that I'm using for inspection. That I want to inspect. 1/4 to 1/2 of the wavelength of the wave that I'm using for inspection. I can resolve that much. Okay, I can resolve 1/4 to 1/2 of the wavelength of the wave that I'm using for inspection. That means what? So when it comes to X-rays, light, lasers, they all have the same wavelength, right? Just about. No, they don't. Their wavelength is different. The speed of light is constant, but the wavelength and frequency are different, right? I mean, X-rays have higher energy, higher frequency, because if I put it in my body, I'll die literally, right? Unless I put it at a very low voltage or something, right? So if I'm using a ultrasonic, so if I have a flaw, which is about, let us pick some number like, let's say 1 millimeter. 1 millimeter is what, 100 microns? 1,000 microns. 1,000 microns. So 10 to the 1,000 microns. 1,000 times 10 to the minus 6 meters. So that means I should use an ultrasonic transducer. A transducer is one which is emitting the waves for inspection. Receiver is one which is receiving, obviously. So transmitter and receiver. So I should use an ultrasonic transducer which will give me a wavelength at least half of this to resolve a crack which is this big. So about 500, the wavelength of that inspection, guys, should be 500 times 10 to the minus 6 meters. So 1 over that is my frequency, because that's my wavelength. My wavelength is that much. So my frequency is 1 over lambda, which is 1 over that, which is, I don't know. Somebody can tell me what it is, then we know what it is. 500, 1 over 500 times 10 to the minus 6. Okay?
This case has happened in India, very recent.
Anji?
This case has happened.
Oh, in India also?
Also.
Yeah. Yeah.
So the same company has to
Shut down everything.
shut down so many planes.
Yes.
For this inspection.
Yeah. Yeah. Absolutely. Yeah. Yeah. Okay. So, कितना हो गया? So 1 over 500, 10 to the 6, 10 to the 8.2. So 2 times 10 to the 7. So 20 megahertz. So I should use a transducer which gives me 20 megahertz signal. Then I'll be able to pick up a 1 millimeter crack length. Okay? So I should be around this range. I don't have to be exactly 20 megahertz. It could be just in the range, right? Because there may be a smaller crack, there may be a larger crack, so I don't have to have exactly. But my tuning frequency could be around this, and I could be back and forth, right? Then I can use that ultrasonic transducer to detect the crack, right? And I'm going to erase this part. So in principle, what happens with ultrasonic transducer? I'm just going to tell you the principle, because I don't know. Okay, so right now, let's put something down. What should I put? Okay. Remember that sound is nothing but elastic waves. If I knock on this thing, what I have done essentially is to make the atoms go like this. That's how the wave propagates. It's an elastic wave, okay? It's an elastic wave, right? So it just goes like that. So here is I'm sending a wave. So this is a rod, okay? And let us imagine there's a small crack here, okay? For a second, imagine there's no crack. We're going to start with a solid body. So I'm going to, and this is my oscilloscope or something. Oscilloscope, amplitude on the y-axis, time on the x-axis. Okay, time on the x-axis. I'm sending a wave. It's going all the way there, and it's reflecting back. So it starts here, goes there. So let us give it some time. So let us say this distance is x. Okay, so it travels as 2x, and then it comes back. And let's say I put a signal there when there's no crack. Now I'll put a crack there. So what will happen is when I'm putting a pulse here, the guys go up a little here and then comes back. Because ultrasonic wave cannot traverse a crack. It cannot go through the empty space there. It will reflect back. That means this is coming back sooner than this signal. This is going longer distance and coming back. This guy is going shorter distance and coming back. But the velocities are same for both. So I'm going to see a signal here, shorter time. So that is my crack, signal from the crack, signal from the defect, because it has traversed a shorter distance and it came back sooner. This is my time axis. So it came back sooner. So this is my back wall echo. This is my echo from the wall, or the back side, or the front side, whatever you want to call. Let's call it as wall, okay? And this is the signal from the crack. Signal from the defect, flaw. Don't have to call it crack, just make it general, flaw. So that's basically your ultrasonic, that's how it works. Of course, I made it very simple, extremely simple. We've got a lot more complications in there. Extreme, very complications. But for our purpose, that's good enough. The only other example I will take, okay, so this will be okay for our blade, okay? But just because we are on this subject, let me just tell you one thing, because I said it could be very complicated. There are books this thick on just this subject. GIAN, I can't remember the guy's name. So this is my pipeline. Long pipeline that's carrying gasoline from Himalayas to maybe down here, Gujarat. Okay, or not, from Delhi to Gujarat, maybe. A pipeline is coming down carrying gas, gasoline, something, you know. So we've got long pipelines that are carrying these things, right? So now, on its thickness, there is a little thickness to it. Okay. Okay, so there is a thickness to this pipe, right? And it goes on and on. So there is a small flaw here somewhere in this thickness due to corrosion. Or maybe here, this is in the earth. This is probably in the earth, right? And this is probably just sticking out just a little bit on the surface, or the whole thing could be in. But the point is, this is on the surface of the pipe. So when I'm using to inspect something like this, I'm better off using guided waves. Guided wave means these waves that I produce, they basically are traveling on the surface. They're very sensitive to surface. So they'll pick up anything that's there on the surface. And there's a special way to produce these guided waves. Okay? Maybe I can, yeah, maybe I can remember that. Okay. So this is what we use when we have pipelines. This was discovered at Imperial College. I mean, a lot of people were working, but those guys are the first ones to patent it, and now we're using this in many places. I'm sure India is using the guided waves. I can almost guarantee that we are using this somewhere in India. It's being used. I'm very certain. Okay? This is a big market, by the way, big market. Because they want inspectors for this all the time. Because the guided wave thing is this. Because these pipes go a long ways, I mean, you may have a mile or half a mile of this pipe, and then you have a weld. And then you have another half mile, 3/4 of a mile, another weld. Because you're making such long pipes, you can't produce a pipe that is 1 mile long. It's not possible manufacturing-wise, so you have to make sections and join them. If not welding, at least you have to put things together and put bolts or something. Corrosion is a big problem, right? These guided waves can go without losing their amplitude or attenuating for long distances. So this is an inspection technique we use quite a bit. And the welding goes along with it at the same time. Okay? These are welded. So if there's anybody who has a problem around pipelines, let me know. We can help them. Okay. So those are guided waves. They can be produced in a certain way. Maybe we'll take up more on this tomorrow, because we got longitudinal waves, shear waves, guided waves. Each one of them has got their own sensitivity, okay? And we can produce, don't worry about this, this thing. Yeah, so they gave a lot of credit to this pilot because she's the first woman pilot, actually, Tammy Jo Schultz, for landing the aircraft despite losing an engine. Woman pilot, okay? So it was a very, very dangerous thing. So women pilots are doing very good. There she is, and yeah, she was all over the newspapers and everything. Big time, big thing. Okay, so what are we doing? Oh, okay, time is up, right? Okay. We'll take up more if you want. So we'll take up more this afternoon. Let me make a selection. Maybe after lunch or something. Yeah. Maybe I shouldn't go for lunch. Maybe stay here. Yes, sir.
We are planning to expand this ultrasonic testing. Means if we can have where to use either A scan, B scan, C scan. That
Right, right.
Overall information, we have this know-how
Yeah,
as a technique.
yeah,
It's really
yeah,
it's for particular kind of damage.
yeah,
Each technique is used and
yeah,
precautions.
yeah. I know what you're saying. Yeah, yeah. It is Professor Arora. Okay.